Hello, this is my implementation of calibrated near-light photometric stereo. So, as a quick introduction, photometric stereo is a way to reconstruct a scene or object by taking multiple photos with different lighting conditions. However, sometimes we have to break the assumptions made in photometric stereo, such as that the light is far away, because the scene might be too small to place the light far away or the object is too large. And as a result, we can't assume the light direction is the same for all pixels and need to consider using near-light photometric stereo. I did this by following the paper Uncalibrated Near-Light Photometric Stereo. Because we can't assume lighting directions anymore, we're back to deriving the following. We can find that the cosine theta of a point x and a point light L is found as the dot product between the normal and the unit vector of the direction. Similarly, because the light isn't approximately constant over all points anymore, we would see that it would actually follow the inverse square law. And plugging these values into the inversion reflectance equation would give us the final equation we see on the slide here. In the calibrated case, we actually know a couple of these terms in the equation. We know the image value, as well as the light intensities and light locations. The things we don't know is the depth, normals, and albedos. To find these, the paper did the following method by iterating and updating the depth every time. First, we start off with an initialized depth by setting all the points to the same depth. Then we find the known part of the equation. This is L of pk, and we can find its relation with the pseudonormal matrix and the image intensities. We can find the pseudonormal matrix by using a pseudo-inverse of L of pk and estimate the normals and albedos from our pseudonormal matrix. And finally, we're able to find our depths by using Poisson integration and updating them. After updating them, we would reiterate over steps 2 to 5 multiple times to narrow down on our depth. So what I need to collect in this situation was images with different lighting conditions, as well as collecting the lighting information, like the intensities and locations. For finding the light locations, I followed the method based on the paper Near Light Photometric Stereo using circularly placed point light sources, where they had multiple reflective planes within the scene, such that the camera could see a specular highlight on each plane from the light. By finding the specular highlight in each plane, the camera can send a ray into the scene and basically find the intersection between the bounced rays to be the light location. As mentioned in lecture, noise would make it such that it's unlikely that the rays would actually intersect, but we can have the following equation solved by using an estimation using least squares. And finally, for finding intensities, we can note at this point, after doing plane calibration and collecting the lighting locations, we would know the normal and light locations for any points on the calibrated planes. So what I did was I selected a couple points from the plane on the white paper surface and found the average EK over multiple of these points. So here are some results I was able to collect. I ran this over 3 different objects and narrowed down on like 2 parts of one object. So we're able to see that we're able to get the normals, depth, and albedos, although the depths might be a little blurry. I also ran these input images through far light photometric stereo, and we have a comparison between the top row being near light photometric stereo and the bottom one being far light photometric stereo. Unlike the paper, I wasn't able to get it such that the far light images had a significant curve to them, and this might be because my light wasn't close enough. But we can see that the depths and reconstruction are pretty similar between both of these, with near light photometric stereo being a little more detailed in this case compared to the far light one. So some limitations I had was with my current setup, I was limited to positions where the light was reflected in both specular surfaces and wouldn't be blocking the object while taking the photo. Similarly, my results might be potentially noisy since I had to manually select the bright points within the specular images. As we can see here, we had a wide range and I wanted to select the center, but it might be off a little bit by just manual calibration. And finally, the paper wasn't clear on how depths would be updated after Poisson integration, since it would only give relative depths, but we needed an offset to get the actual depths. So I ended up handpicking those as well. Here are the references I used, and thank you for listening.